Welcome back. The objective of this video is to do more advanced transformations of our parent sine and cosine functions. On the left-hand side here, we can see we have our function for sine, y equals a sine of b times the quantity x plus c plus d. And our key points here are shown graphically on the right-hand side, where we've got our starting point. Our amplitude is listed here as a. This appears to be a positive sine function. Our period is the length of one cycle. That's 2 pi divided by b. And then we'll have a finish line, which would be whatever the period is after the start, which might have some phase shift in it. And our midline is y equals d. Lately, that has been at y equals 0, but the d will shift that up and down along the y-axis. I do like to use like x minus c here, and that's consistent with our phase shifts then become the opposite of what we're looking at here sine-wise, and that's consistent with what we've done in the past. Our key points, we're going to steal our key points from the unit circle, from the quadrantals. We're gonna graph, the quarter pole, the start, the quarter, the halfway, 3/4, and then the finish. We'll do our 5 key points. If a is greater than 0, our amplitude is positive, we'll follow our parent sine function and go in the positive direction to begin with. Gene Adams likes to show that we have a max. Actually, we start at an intercept. Let's correct that. So using our quadrantals, we start at an intercept at 0, and then it goes to the max. In sine, it's 1, back down to an intercept, to our minimum, and then back to an intercept. Now, when a is negative and we reflect our graph over the reflected over the x-axis, we follow a similar pattern. We still start at 0 or at an intercept, but then since we go in the negative direction, we go to a minimum, back to an intercept, and then we go to our maximum, and then back to an intercept again. So kind of going in the opposite direction, if you will, if a is negative. And then our cosine function, y equals a cosine of b times the quantity x plus c, all plus d. And again, we have the same kind of thing where the plus d, that's going to be our midline. We're going to have a start. Our amplitude is a. Our period is still 2 pi over b. And we have our start here at c and our finish here, and that we go through one cycle. And again, we're going to steal our key points from the quadrantals on the unit circle. When a is greater than 0 or a is positive, we're going to start at 1, right? On our unit circle, the cosine of 0 is 1, and sure enough, we'll start at 1 unless we have some sort of amplitude to multiply that, but we'll start at a max. And then at the quarter pole, we'll have an intercept. And then at our halfway point, we'll have a minimum. And then at 3/4 pole, we'll have another intercept. And then on our finish line, we'll be at our maximum again. And then if a is less than 0 or negative, well, we'll start at a minimum. So minimum, intercept, maximum, intercept, and then minimum. So we would start down here, and our cosine function would look like something like that if a was negative. So a little review here. Our amplitude, the absolute value of a, changes the height of the graph, right? Our 1s will become 2s or 3s or 4s or 1/2. Our period is 2 pi divided by b for sine and cosine. It's the length of one complete cycle. It's one loop around the unit circle. Our phase shift, the opposite of c, is a horizontal translation or our starting point. If we do minus c here, then that would just be a positive. So we'll go through those and then we'll see that those are similar to what we've done before. Our midline, our vertical shift, our d will shift up and down the y-axis. Our b value is the number of cycles in the interval from 0 to 2 pi, and we'll use that to help us find our period and also our frequency. And b times x plus c, this expression is called the argument. Now sometimes you'll see this distributed in bx plus bc. We may have to factor that out at times as well to help us out. Let's go ahead and graph. In example 1, y equals 3 sine of 3 times the quantity x minus pi over 6. We don't have any d, we don't have any change in our midline, so our midline is going to be y equals 0. We've got an amplitude of 3 from our a value. And we also have a b value of 3. So our b value is 3. So our period then is 2 pi over 3, or 2/3 pi. And we also have a shift. We have a phase shift of pi over 6 to the left. Oop, I beg your pardon. That's actually to the right. We have a shift of pi over 6 to the right. So the opposite of what we're looking at, just like what we've done before. So pi over 6 is going to be our starting point. So we're going to start at pi over 6. That's going to be our starting line for our graphing our sine curve. And I think this is really important, is knowing where our start line is after our phase shift. And since our period is 2 pi over 3, or 4 pi over 6, our finish line then is going to be pi over 6, our start line, plus our period. And our period here is 4 pi over 6. I just got a common denominator, so it's easier to count. And now we're going to finish at 5 pi over 6. So we're going to graph our entire sine curve between pi over 6 and 5 pi over 6. We're going to divide this into our quarters. So we'll want to know what halfway is, and then what the first quarter is, and the third quarter, and then the finish. So let's think about our sine curve. We start at pi over 6, and the sine has a value of 0. And we're going to finish at 5 pi over 6, and we're going to end up back at 0. So what's halfway between between pi over 6 and 5 pi over 6? Well, 3 pi over 6 is halfway in between. So our sine curve, again, is going to have another intercept at 3 pi over 6. And then at 2 pi over 6, we're going to have our maximum. Think about your unit circle, right? When we start our sine curve, we are at 0 and then at 1, but we have an amplitude of 3. So at the quarter pole, sine would be 1, but now at our quarter pole, the sine is going to be 3. And that is going to occur at 2 pi over 6. And then at halfway, the sine is 0. And at the 3/4 pole, the sine is -1, but we're going to multiply that by 3, so we're at -3, and then the sine is back at 0. So now we have graphed one period of that sine curve with its transformations. In example 2, we're going to graph this cosine curve. This one has an amplitude of 2. So our amplitude's 2. We've got a b value of 1/2. That's going to impact our period. And we have a phase shift left of 2 pi. So our amplitude is 2. Our b is 1/2. So we have a period of 2 pi over 1/2, or we have a period of 4 pi. So now we've stretched out one cycle. Instead of between 0 and 2 pi, it's going to go all the way through our 5 points between 0 and 4 pi. Because we have x plus 2 pi, we have a phase shift of 2 pi to the left. So that means our new start line is at negative 2 pi. And our finish line, after we complete an entire cycle, is going to be negative 2 pi plus our period of 4 pi, which is a finish line of positive 2 pi. So we'll graph all 5 points between negative 2 pi and positive 2 pi. So our start line is going to be at negative 2 pi. We're graphing the cosine curve. So on the unit circle, the cosine at our start line is 1, but we have an amplitude of 2. So instead of starting at 1, we're going to start at 2. And halfway through, we're going to graph the whole sequence between negative 2 pi and 2 pi. So the origin is going to be our halfway point, and our finish line is going to occur at 2 pi. So when I go all the way around the unit circle, I'm back at 1 with an amplitude, so I'm back at 2. So halfway around, I have a cosine of negative 1, but times 2. So that would be negative 2. And my quarter poles then are pi and pi on our xy axis, but my quarter pole, the cosine is 0. And the 3/4 pole, the cosine is 0 again. And here is one cycle of y equals 2 cosine 1/2 x plus 2 pi. Here we're asked to compare and contrast what occurs to the period when b is greater than 1 to when b is between 0 and 1. Well, we saw in example 1, our b was 3, and that compressed our period, or our sine curve. So b is greater than 1 is going to be a horizontal compression. And when b is between 0 and 1, and I need to correct my inequality here, we have a horizontal dilation. So when in sample 2, b was 1/2, and that extended that out, that doubled the length of the period. So I'm going to go ahead and correct this guy now. There you go. There's the correct inequality. And then write an argument when c is less than 0, then the phase shift is to the right. And when c is greater than 0, the phase shift is to the left, just like we have done in our past studies. And then finally, the vertical shift, or the midline, when that shifts, that becomes our new 0 line. So here we're taking our d value and taking y equals 0, and we're shifting it up to y equals 1. But that becomes our new 0 line. Those are going to be, for sine, those are going to be the zeros, or our start, and our halfway through, and our finish when we go around the unit circle. And then for cosine, in this one we shifted down 2, so we have a y equals negative 2. She uses x prime here to show that this is our new x-axis down at negative 2. So think of that as our new 0 line. And finally, in example 5, the summary below, the amplitude is given by a, and the amplitude is half of the height of our sine or cosine wave. It's a vertical dilation, and it's the height above the midline. Our period is 2 pi over the absolute value of b. It's the length of one full cycle. Our phase shift is c, a horizontal shift, the first key point of a cycle, or we might say like the start point. And then the vertical shift, the midline, moves the x-axis up or down. I call it our new 0 line as well. That's our first look at transformations of sine and cosine curves, and we'll get some more practice with this when I see you in class.